Hi, this is the Math 127 review, and we will be doing review question 1 today. So that is, we are going to be calculating the work done by the vector field, which is 2z e to the 2x plus y squared, comma 2xy, comma e to the 2x minus 2z, in moving a particle along a path from 0, -1, 2 to 1, 3, 0. Okay, and so we have to recall that work is this line integral. And so the first thing that we're going to do now is, because I'm not really seeing a path, so the first thing that I want to do is check whether or not this is independent of path. And so to do that, we have to make sure that the curl of the gradient vector is equal to 0. And in this instance, the gradient vector is the vector field that's provided to us in the question. And so what we're going to do is find the curl of that. So we have to set up our matrix. We have our I, J, and K. And then we have our partial with respect to X, our partial with respect to Y, and our partial with respect to Z. And then from there we can just fill in our vector field. Plus y squared. 2xy and e to the 2x minus 2z. Okay. And so to do that, first we have our I, and then you're looking at this part of the matrix. So you have your d dy for e to the 2x minus 2z. And then you have minus your partial with respect to z for your 2xy. And then we have our minus j, and you're looking at this part and this part. So we have our partial with respect to x again, for our e to the 2x minus 2z, minus our partial with respect to z, for our 2z e to the 2x plus y squared. And then, last but not least, we have our k, and then we're looking at this part of the matrix. So, our partial with respect to x, so 2xy minus our partial with respect to y for our 2z e to the 2x plus y squared. Okay, so looking at this now, when you take your partial with respect to y, what you're going to do is hold all the variables that are not y as constants. So here we have our e to the 2x, and so that's going to be treated as a constant, and that's going to go to 0, as is our minus 2z. And here we have our partial with respect to z, and since I don't see a z here, just 2xy, all of those are going to be treated as constants, and it's going to go to 0. And here we have our partial with respect to x, so we have e to the 2x, so that's going to become 2e to the 2x, and then our minus 2z is going to go to 0. And then we have minus our partial with respect to z of 2z e to the 2x, and so what's going to happen here is that it's going to get rid of our z and just give us 2e to the 2x, and our plus y squared is also going to 0, and since we have this subtraction sign here, these two are going to cancel each other out, and this portion is also going to become 0. And finally, for our k, we have our partial with respect to x for 2xy, and so that's going to become 2y, and then we have that minus our partial 2z e to the 2x, and since there's no y there, that becomes 0, and our derivative of y squared with respect to y just becomes 2y, and again, the 2y and the minus 2y cancel out, so that also becomes 0, and so what we have here is the 0 vector. And so we know that this is a conservative vector field, and we can solve the question going from there. So now that we know that our vector field is conservative and it is smooth, we can use the fundamental theorem of a line integral to find f and to figure out the work that was done. So what we're going to do is we're going to take the integral of each component with respect to x, with respect to y, and with respect to z. So the first part, we're going to take the integral of 2z e to the 2x plus y squared with respect to x. And so to get that, the first part is going to be z e to the 2x plus xy squared plus whatever our constant is, which would be something that would have a y or a z in it but no x, so that when you take the derivative of this part with respect to x, it should come back to be the x component. So, okay. And so we'll take the integral of the y component with respect to y, and that is x y squared plus some constant in terms of x and z. And finally, we will take the integral of the third component, e to the 2x minus 2z with respect to z. And so that would be z e to the 2x minus z squared plus some constant x and y. All right, so now looking at these three that we have, what we're going to do is figure out where things overlap. So we have z e to the 2x here, and we have our xy squared here and here, and then we have our z, which is minus z squared. So our scalar function f is z e to the 2x plus xy squared minus z squared. And so what we're going to do is we're going to plug in these endpoints to figure out the total work done. So we found our f of xyz is equal to z e to the 2x plus xy squared minus z squared, and so what we're going to do is plug in our final and initial points to find the work done. So we have our f of our final point minus the f of our initial point. And this is just plugging everything in. So we have our z, which is 0, e to the 2x, which is 1, plus x, which is 1, and our y, which is 3 squared, minus our z squared, which is 0. So we have that entire quantity minus our initial. So we have our z of our initial, which is 2, e to the 2x, which is 0, plus x, which is 0, our y, which is negative 1 squared, minus our z squared, which is 2 squared, to the entire quantity. So for our first part, it is 0, and then we have our 9, so yeah, 9 minus 2 e to the 0, which is 1, so that's 2, 0, 2 minus 4, so negative 2. And we get our final value as 11. All right, so to summarize what we've just done, we calculated the work done by this vector field, and so we had to use this line integral. And so when we did that, we had to consider whether or not it was independent of path. And so to do that, we took the curl of the gradient vector, which is this, and then we found that it was equal to 0, so we could go from there. And so we found a scalar function such that the gradient of that scalar function is equal to the vector field that was given. And so once we did that, we found the partial integral with respect to each component, and then we compared and we found where it overlapped to find our scalar function. And once we had that, we could use the fundamental theorem of a line integral to plug in our final and initial points, and then doing that, we found the work that was done. And the units for this would probably be force times some sort of distance, so like for example newtons times meters. And that is it.